L, right? So from that we can judge that the inductor current will rise linearly from 0 to dTs up to the on period. When the switch is off, the diode will be on. In that case, the voltage across the inductor will appear to be minus V naught. As the voltage across the inductor is negative, so that's why the inductor current will decrease linearly up to the point when up to the turn of time. Okay, so we can go from here that we'll find the values of L and C, right? That is the design specifications. So for L, we will first see that our converter should work in the continuous conduction mode. For our converter to work in continuous conduction mode, the ripple should be less than the average value of the inductor current, right? So del IL by 2 should be less than IL average. What is IL average? IL average is basically V naught by R, correct? And del IL by 2 we can find from this graph, that is that will be L dIL by dt equals to the voltage across the inductor. By solving those equations, we can get these two formulas. That is for L and for C. For C, we will go through the we'll um, shift this graph downwards, and then we can find the area across the upper triangle. That will be half into T by 2 multiplied by the height, that is del IL by 2. And from there, we can substitute the del IL value and we can find the value of capacitor. We have calculated the values of the inductor and capacitor according to our parameters. We have taken the output power to be 500 watts and the input voltage to be 100 volts. Output voltage will be 50 volts because we are taking duty as 50%, right? So the output voltage upon input voltage will give the duty ratio. Then the load resistance we have taken is 5 ohms. And from all these values, we have calculated the value of inductance and capacitance, that is 5 millihenry and 5 microfarad. The switching frequency is assumed to be 50 kilohertz. We can take any value of switching frequency, but here we are taking 50 kilohertz. Next. This is the basic Simulink model for our buck converter. As you can see, we will be going through this buck converter from the simulation as well. You're able to see the simulation file, right?
Yes, sir. Yes, sir.
Yes, sir.
Just give it a second to load. Okay. So this is the basic buck converter that we have designed, the Simulink model of the buck converter. Here we are using the bus generator to provide the duty to the MOSFET, and the input voltage is 100 volts magnitude, and the values of inductance and capacitance as I have already shown. The inductance is around 5 millihenry and the capacitor value is 5 microfarad. All right, so we can go ahead and run this. As you can see, the output voltage is around 48 volts. This is the inductor current value, and this is the input voltage. The input voltage is 100 volts, and the output voltage is nearly 50 volts. There's some difference because of the drops in the resistance drops. And yeah, this is the basic buck converter. We can now move on. Okay. So here we conclude our buck converter journey. Now we will next move on to the design of its gate driver, right? So why do we need a gate driver actually? We want to give the MOSFET some duty ratio, right? Some pulses. It will be turn on and turn off for certain time. So in order to do that, we will be using a microcontroller. We will be programming a microcontroller such that it will provide on it will provide high pulse for some time, and then it will provide off pulse for some time. But the output of a microcontroller is usually from 0 to 5 volts or 0 to 3.3 volts, which is not enough to drive the gate circuit, gate of the MOSFET. Usually the gate of MOSFET requires around 10 to 15 volts. Okay. So we have to shift the level of this microcontroller output voltage from 5 volts to around 15 volts. So for that, we will be using this gate driver circuit. So this is the basic schematic of the gate driver circuit. You can see that we are using this TLP250 IC. Okay, so let me first explain this IC to all. So this is the basic configuration of this TLP250 IC. It consists of a IR LED. This IR LED will emit IR light onto this photoreceptor. Whenever this receptor receives light from this IR LED, it will produce some voltage difference across the inverting and non-inverting terminal of this op-amp. As we know that op-amps have very high gain ratio. So whenever a small voltage appears across its input, then the output of the op-amp will either saturate to plus Vset or minus Vset. Okay, whenever this op-amp's value goes to plus Vset, our amplifier circuit will be triggered, and the voltage across this will appear across this sixth and fifth terminal. You can see that sixth and fifth terminals are shorted. Eighth and fifth terminals are for providing the external voltage of around 15 volts. 1 and 4th pin are redundant pins. 2 and 3 pins are the microcontroller pins, or the from inside you can see that is IR LED pin. So whenever 5 volts will appear across this IR LED, it will turn on. Okay, so this is a basic schematic of this gate driver circuit. Yeah, any problem? Okay. So you can see that just a second. Yeah. So you can see there is a input resistance. This is to limit the current, because this is a LED, right? So if too much voltage will appear across it, then it can burn out. So in order to limit the current, we are using this resistance, input resistance. Then there is a supply voltage source. This will actually provide the power required to turn on this gate. Then there are, you can see there are two capacitors. One is a non-polarized capacitor and another is a polarized capacitor. This unpolarized capacitor is basically for filtering the noises out. This is a decoupling capacitor. And the other polarized capacitor, this is the, actually it has higher values than the unpolarized capacitor. And this is mostly used for storing the energy from this battery source. For during fast switching, we need the gate driver to turn on and turn off faster, right? If we don't have enough current flowing through this gate driver circuit, because if you know that if you know about MOSFETs, then this the gate and gate terminal circuit inside the MOSFET, it appears like a capacitor. So if the switching frequency is too high, then the current may not be sufficient enough to turn on this MOSFET. Voltage across this gate terminal is not sufficient enough to turn on this MOSFET, right? That's why we are using this higher value of capacitor. in order to provide that voltage change across this. Then we have a current limiting capacitor, that is 10R, and we have a this resistance, and whenever this gate pulse, it will receive the gate pulse from the microcontroller. This IR LED will turn on, and in response to it, this amplifier circuit will be triggered, and this voltage source will provide the required gate voltage in order to turn on this MOSFET. I think we are clear with this, and we can move on. So we will be designing this gate driver circuit using Kicad. Kicad is basically open source software. I hope we all have installed our Kicad softwares in desktop or laptop on whichever system you have. Hello?
Yes, sir. Yes. Yes, sir. We have installed in the.
Great. So I will be skipping the installation portion from here, and we'll directly jumping into this Kicad library. So let me open up my Kicad. Okay. So when you open or launch this Kicad software, then you will be landing on this front page. Here you can see there are many icons or many tools that we can use. First one is schematic editor. So schematic is basically the same thing that we do in Simulink. We will use the symbols
Sir,
of
your
this
voice is not
components.
clear, sir.
Okay.
Sir, your voice is not clear.
Now is it okay? Hello?
Sometime it is blurring.
Okay, sorry.
No, Shashwat, it's fine. No, Shashwat, it's fine. It's fine.
It's okay. Oh, thank you. So first we will go through the schematic editor. So what is schematic? It is basically we will be using the symbols of the components in order to design our circuit. It's more or less like the Simulink that we use, how we design circuits in Simulink. Next, we will be going to symbol editor. Let's say actually there is a default library of symbols inside Kicad. Let's say we want to add a component whose symbol is not present inside the default library. So we can create our own symbols using the symbol editor. Right. Next, we will be going to PCB editor. So PCB editor is basically the tool that will enable us to actually specify where the position, location, and size and dimensions of the holes that we required on the PCB in order to place our components. Got it? So that will actually decide how our PCB will look and it will function. The main aspect of the entire session is to design this PCB. While designing a PCB, we should keep some things in mind, like it should be as compact as possible. We are designing the PCB. That is the main objective. Why are not using the breadboards, right? We are doing all these things in order to make the size compact. Day by day, we are seeing that the size of phones and laptops are reducing and their computational powers are increasing. That is also an example of reducing or optimizing the size of a PCB on a smaller form factor. Okay. The next we can move on to the footprint editor. What is a footprint? Footprint is basically the actual dimensions or the physical dimensions of a component that will go into our circuit board. Let's say capacitor. Capacitor has two legs, right? So the footprint will contain the distance between the two legs or the distance between the holes that will drill into our PCB in order to place that capacitor. Next is Gerber. What is Gerber? Gerber is basically like a communication medium that will tell our PCB manufacturer about how and where and the location of the drills that he have to make in the PCB, the paths of the or the traces that he have to make. Okay, so it is basically the kind of language that will use to communicate with our PCB manufacturer There are many PCB manufacturers. I think you might have heard about JLC PCB or PCB Way. So these are some of the most famous PCB editors, PCB manufacturers that will help you to bring your circuit into life. Then there are some calculator tools. Let's say we have to calculate some parameters for your circuit, then you can use that. Then there is a drawing sheet. So what is a drawing sheet? Basically, we will be designing all our circuit and schematic on a blank canvas, and Kicad likes to call it the drawing sheet. Okay. So this is all about this panel. We can go to the left hand side. If you see, there are some icons here. If you will go ahead and click on this new project, then you will be prompt to ask, you will be prompt to give the name of the project that you want to make, right? So I will go ahead and type, let's say, Kicad demo and click save. After I have given the name of my project and clicked save, you will see that there are two files that are visible here. One is kicad_demo.kicad_pcb and another is kicad_demo.kicad_sch. This .pcb folder is basically for the PCB editor. It will take us to the PCB editor, and this kicad.sch, this folder, this file is for the schematic editor. All right. If you think that I'm going too fast, or if you feel like I'm going too fast, you can ask me to slow down so that you can catch up. Are you following?
Yes, sir. Yes, sir.
Okay. So great. Now go ahead and click on the schematic editor. When you click on the schematic editor, you will be landing on this page. Try to get familiar with this page. If you scroll in, you can zoom in, scroll out to zoom out. You can click on the right click and drag this in order to drag your whole canvas. If you want to select any component on this, you can left click and then select it. And in the bottom left right corner, you will see that there are some placements that you can fill out. In order to fill this, you can go ahead and click on this page setting icon from the left hand top corner. There's a page setting icon. If you click on this, you will see that this screen pops up. Here you can set the different dimensions of your page. Let's say you want A5, A4, A3, or any dimension you want for the page that you want to print on. There is a preview panel where you can see the changes that you are making. You can save this file onto some folder that you can click here and select your directory where you want to place. Then there is an issue date. Let's say I want to place today's date on this. So I will click on this 3 lesson symbol, and today's date will appear across this issue date. Next is revision. Let's say we are making this our PCB. So sometimes we make mistakes and we want to rectify it. Let's say this is our first revision, right? We are making this PCB for
Sir,
first time. So,
hello.
yeah.
Sir, can you please go slow?
Yeah, sure.
Because,
Yeah. So we are on the space setting, right? You are on this here or okay. So I will put this revision 1 because we are making this for first time. Let's say you are rectifying the circuit for the 3rd or 4th time. Then you can put 3 or 4 or any value you want. Next, we will go to title. Let's say you want to give the title of this project. As I said, Kicad_demo. So this will be the title of our project. Next, company. If you want to give the name of a company, you can definitely go and do it. I will go ahead and write NIT Rourkela, and then you can click OK. So you can see whatever details I filled on that, they appear here, right? So are we on the same page now? Are you able to follow here to this point?
yes.
Yeah, great. So okay. So you can see there is a plus sign on our cursor. It is actually called crosshair. If you have played any games, you might have seen the crosshair on your any guns or anything you you are using that. So this is similar to that. On the right hand side, we can see there is a open symbol. If you'll click on it, then okay, give it time to. Okay, so after clicking on that, you will see that the screen pops up. So this is basically the default library of symbols of Kicad. Here we can find all the components that we want to add into our schematic, right? So let's say I want to add a register. So I will type R. By typing R, we can see that our register symbol is here. There are different register symbols to choose from. Let's say we want to add a variable register symbol. And there is a variable register for this. Then there are different register types. You can choose whichever you want. So we can add this, right? So there are different symbols. We can go and see capacitor value. So this is capacitor. Then let's say inductor I want, then I will press I. I press L to get an inductor. Okay. And then let's say I want MOSFET. And you can see there are many MOSFET symbols and MOS, PMOS and all. Okay. Let me close this for now. We will get to that later. Then next, there is a power symbol option. If you click on this, for the first one, that op-amp symbol icon, that was for generic components, and this ground symbol, this library is for power symbols. Like we want to add a 1 volt source or 1.1 volt source, 1.2 volt source, or any voltage for that matter. Let's say I want 1 volt source in our 1.1 volt source in my circuit. I will add this 1.1 volt, and let's say click on this. I can actually edit the value of this, and I can, let's say I want to put volts. So for now, let me go ahead and delete this. Then the third, you can see there is a draw wire symbol. Let's say we have already made our arranged our components in the right places where we want them. Next, we will go and click on this draw wire symbol, and we can draw the lines or the paths that we want to connect and the wires that we want to connect. And one more thing in this panel is this draw areas. Okay, if you click on this, you will be able to draw a certain area that you want, like this. And okay, so I will be drawing this area. Let's say there are 2 or 3 schematic diagrams on your canvas. Let's take an example. Let's suppose you are trying to design the circuit of Arduino. So what are the components that Arduino contains? It has a microcontroller. Then there is a analog to digital converter. Then there is a power circuit, right? So if we will draw everything in one place, then it will be very cluttered and messy, and we won't be able to debug it if there is any fault. We won't be able to read that circuit properly. So for that, what we will do is we will design each part of the circuit in a different separately, and we can place this areas over them so that you can differentiate between each part of the circuit. Okay. So that's all from this right hand corner. For next, we will go to this top corner. Here you can see there are different icons again. The first one is symbol editor. We have already discussed the symbol editor before. It's the same thing. You can move into the symbol editor page from here also, and from the front page as well. The next is symbol library browser. We can check the library or default library of Kicad from there. Then there's footprint editor. Let's say we have a component which is quite new compared to this Kicad. So the footprint library of Kicad doesn't have that specific footprint for your component. So what we can do, we can actually design that footprint from our own side. You will need the datasheet for that component. You will open the datasheet and see the physical dimensions of that specific component. Then by using this footprint editor, you can create your own footprint for that specific component. Then there is node schematic. So it's basically it's kind of a debugger, or it's kind of a compiler. If you have written any program, then you know what is a compiler, right? It will validate the entire circuit, and let's say there are some open ends, like open circuit, or there are some short circuit. Then this tool will help us to know that there are some errors. Then there is a simulator as well. If you have designed your schematic, then you can simulate the circuit from here as well, just like as you do in a Simulink. Then there is assign footprints icon. From here, we will be assigning the footprints to the different components that we'll be adding in our circuit. Then there is generate bill of materials. So bill of materials is basically what it will do is it will generate, it will give you a Excel file where the different components will be listed, so that you can purchase them. Okay. Next is the PCB editor. From here, you can go to the PCB editor page. Okay. So this comprises of all this. Then there is from here you can print our circuit, and here you can see there are three options. There is for inches, there are mils, and there is millimeters. I suggest you stick to mils, and the grade should be 100. Okay, you can change them, but I suggest you stick to 100 for this specific circuit. Okay, so that's enough for this introduction. We can move on to designing our circuit. I suggest you open the circuit diagram of the gate driver circuit. That is this one, this circuit, and put it on a corner so that you can refer to it whenever you want. So I'll go ahead and minimize this. So you see there is a TLP250 IC. So first we will import that TLP250. Okay, so you don't always need to go here and then click here, then the library will open up. You can simply click, press A on the keyboard, and that will automatically open up this library. Here I will search for TLP250. Okay, so here this TLP250 is here. You can see the symbol for that. If I click on this and click OK, then you can see it is on my cursor. So wherever you want to place, let's say I want to place my TLP250 here, then position your cursor there and then click OK, and it will be placed here. Okay, I can click on this and then drag it anywhere I want. Some shortcuts are there. Let's say I want to rotate this symbol, so I will click on it, select it, and then press R on my keyboard. Pressing R, we can rotate this. Let's say I want to flip this in x-axis, then I will click on this and then press X in order to flip it. Okay, see, I can flip it on both sides. Okay. Then next we want some resistors, right? So I will press A again. This will open up this. Press R, and this resistor. I will add this to my circuit. Then I need some screw terminals. So screw terminals are basically, okay, so we want to give the gate pulse from our microcontroller, right? So we will be using jumper wires for that. So where do we put the jumper wires in the circuit board? So in order to put the jumper wires, we need the jumper pins on the circuit board. Correct. So for that jumper pins, we will be using the screw terminals. So here you see screw terminal 1x1, then there is screw terminal 1x2, then there is screw terminal 1x3. What are these? These are basically the number of pins that you will get. For 1x1, you will get a single pin. For 1x2, you will be getting 2 pins. 1x3, you will be getting 3 pins, and so on. So for my for this specific project, we will be selecting this one cross two, and then click OK. See here you get this screw terminal block. Then we need capacitors, right? So I will be typing capacitor C, and say this is the unpolarized capacitor. I will be needing this for the decoupling capacitor. Click on this and place it here. Next, I want a polarized capacitor that will help us in transferring the voltage or changing the voltage for on a rapid speed. So let's type C here, and if we go below, you see there is a polarized capacitor, right? There is a plus symbol on top, so it is basically polarized. Click on it, and I will place it here. Okay, so I think that's all the components that we need. You can go ahead and verify it. There are some capacitors. There are this resistances. We will copy that and paste it again. Then there is this resistance. We are not going to add any battery in here because we will be giving supply to our PCB from external voltage source. So for giving external voltage, we will be using the jumper wires again. For in place of battery also, we are going to use the same screw terminal block. Okay. So you can play around with it like pressing R and pressing X. You can flip it and rotate it. So let's copy it again. Control C. Will be one here, one here. Then we need this resistance for. We want this terminal to be flipped, right? We will give the input from this end. So click on it and press R in order to rotate it, or sorry, or press X in order to flip it. And this resistance we have to copy it because we need two resistances in this side. Okay. So I think that's all the symbols that we need in order to make our schematic. So click on it, press R in order to rotate it. I will be placing it here. This one I have to rotate it in other direction like this. And okay, so either you can go here and click on this draw wires option in order to start drawing wires, or you can simply bring your cursor near to this end and you will see that a pen symbol appears on our cursor. You can just click on it, and then you see by extending our cursor, we can see that lines appears. You can go ahead and connect this to this resistance. Then again, you will click on this and connect this, and this will be connected here. This you can connect like this here, then here. Okay, let's say I will placing this here. This will go here. You can connect these symbols as per the circuit diagram, like you do in a Simulink model. It's pretty easy for that matter. We will be sorting the 6th and 7th terminal, and let's say I place it here. Okay, so we are done with our schematics. Are you able to draw this? Yes. Okay, fine. So after drawing this, I'm audible, right? So all right.
Audible.
So
But
yeah,
not designed full all.
okay, you are not able to design it. Hello.
To design, but I have not completed what you have. I am able to design, but not completed as you have completed.
Okay, so you want me to wait for some time, or
You go because recording will be available on the YouTube.
okay, sure, yeah, fine, great. So
Okay.
so here we have designed this entire schematic, as you can see. It's pretty simple. It's just same as the Simulink how you draw that. You can refer to the circuit anytime you want. I have done this 2-3 times. That's why I remember
Sir,
this. Yeah. Go ahead.
excuse me, sir.
Yeah.
Sir, here that some wire is crossing to each other. How to identify whether it is crossing or it is a junction? Means connected.
See, there is no dot here, right? Let's say this wire is crossing this, but there is no dot here. So it's not overlap. It's not connected.
Okay, means dot will identify this is connection.
Yeah. Let's say, okay, I'm showing you. Okay, let me delete this, and I will just connect from here to here and then from here to here. See, there are two dots now. So that means that this point is connected to this. But if I will directly connect this to here, so now there is no dot, right? So that explains your problem, I guess.
Ah, okay, sir. Okay, sir.
Yeah.
But
Yeah.
here also the first point is not no doubt no dot starting from the bottom. Fifth.
Which one? Fifth, yeah. From
Uh,
fifth, where to go?
fifth one to that capacitor.
Yeah, this is not connected. No, we don't want to connect this. Are you getting? This is separate
Okay.
wire. This is the output wire. See here in the schematics, this one is not connected, right?
Yes, sir.
Yeah. So this is the entire schematics. If you are you are able to follow, then that's fine, or else you can refer to the video later. Then we will click on this resistance. Let's go ahead and click on it. So you will see this screen pops up. So the first thing is reference. So what is reference? Let's say you are drawing a circuit. So there are, let's say, 4 or 5 resistances. So how you denote them? Like R1, R2, R3, right? So it's basically the same thing. So this is the reference symbol. So if you want this to show in your schematic, then you can check this, or else you can uncheck this. For now, for simplicity and cleanness, I will uncheck this. Then there is value. You see from the schematic, the first value of this resistance value is actually 1 kilo ohms. I think it is not mentioned here. So you can put 1K and then click OK. See you see here 1K appears. Then next you can go to this C1. This is the unpolarized capacitor. So I will uncheck this again. Usually the unpolarized capacitor or the decoupling capacitor, its value is smaller compared to the power capacitor. So I will put here, let's say 100 nanofarad. Okay, and click OK. The next is the polarized capacitor. If I will click on this, and its value is actually 100 microfarad. What you will choose? Okay. Okay. So this is 100 microfarad. This is 100 nanofarad. Let's say I want to put the value of this resistance, and it was around, I guess, 10 ohms. Yeah, 10 R. So can click on here. This is 10 R. Click OK. This is 10 R. Then its value is around 1K again. Yes, okay. So yeah, this is how you can change the values or assign the symbols if you want. If I will check this, then you can see the C2 will appear because the reference value of this capacitor is C2. If I uncheck this and click OK, then that will disappear. Okay. After we are done with this, we can go ahead and click on this anode schematic. If you click on this, this page will appear. And if you click on this anode, then it says annotation complete. So let's say you have some open-ended wires, then it will show some errors. Okay. So if you are having any errors, then you can debug your circuit. There are some problems in your circuit, then you can rectify them. And then again, click on anode, then you will see this anode complete. This is basically the green symbol, that green sign that you can go ahead. The circuit is fine. There is no problem with the circuit. You can close this. Then we will go to the footprint assign. Okay. Here you can see there is a icon. There is assign footprints. If you click on this, this will open up this page, and all the components that we have added in our circuit is listed here. There is C1, C2, then the screw terminals, all the 3 screw terminals. Okay, let me actually go ahead and give this screw terminal some names. I'll remove this one, and this is the microcontroller input, right? That's a microcontroller. Mu C. There's a microcontroller input terminal. Then let's say this is the power terminal, right? So I'll go here and then here, yeah, 15-volt in, or I can just type VCC. So here you got there is VCC. Then there is this here for the gate driver. So it will be, yeah, gate out. Okay. So from here we can take the output to the gate circuit, and from here we'll be giving 15 volts input, and from this side that is the microcontroller input. Now if I click again, I will click on anode. It shows the correct symbol, and then we will go to assign footprints. Here you can see everything is listed, whatever we have added in our circuit. So let's say first we are going to add the 100 nanofarad one. So remember 100 nanofarad is the smaller one, so it is an unpolarized capacitor, right? So for unpolarized capacitor, if you will go to the PPT, I have given here the, yeah, here are the footprints names. Okay, generally you will find these footprints in the datasheet of each and every component that you are adding. You can find them in the datasheet, or you can create your own footprints as well. Creating one footprints will actually take a lot of time and energy. In general, we can repurpose the different footprints. Let's say I have a 8-pin IC. So in general, the manufacturer ICs, all the 8-pin ICs, they have the same dimensions usually. In case it is off course, then you can print a custom footprint for that, or else you can repurpose other footprints from other components. Let's say I have made my own IC which have 8 pins, and then I can use the footprint from an existing IC that have 8 pins. Okay, so we were placing the footprint for the unpolarized one, right? So this generic capacitor, I will copy this from here. Copy this from here, and I will go to capacitors from this side. You'll find. Okay, so here you see there are 3 capacitors: capacitor SMD, capacitor SMD, and then capacitor THD. So these are actually 2 different types of capacitors. One is SMD and one is THD. So what is SMD? It is surface mounted device, and THT will be the general capacitor that you see in the shops or that we use. Okay, let me show you what a THT and you see, these are surface mounted devices. Those are very smaller, and for compact circuits we will be using them. This is a great example for that. These are the these are the THT sim components, and these are the surface mounted components. Okay, so there's a difference. So for this we will be using THT. So click on capacitor THT, and from this here, this space, you can paste the value that we copied from that table, and you see here the footprint is there. You can double click on it, and will be assigned to that specific component. And there is C2, that is polarized capacitor, right? So again, I will go to that table and I'll just copy this, go here, and then again I will paste it here. See, the capacitor for the footprint for polarized capacitor is here. So I will double click on it in order to assign that. Then we need the junctions J1, J2, and J3. For that, you will go to the terminal section, terminal block, click on this, and then again go to here, then this screw terminal, this copy this, go here, then Control A and E. So here you see this appears, this footprint. Again double click on it in order to assign this to this junction J1. Again double click on it, and again double click in. So these three junctions, we have assigned these three terminal blocks or these three footprints to them. Then we'll move on to the resistance. Again the same thing, generic register, copy this, then go to this, and then find the resistance THT from here. See, there's resistors THT, click on this, and again go here and paste the copied value and double click on it now to assign them. Now see, all the components have their specific footprints assigned to them. Now you will be wondering why we didn't assign the footprint to the TLP250. So it is already assigned by Kicad because it is special kind of IC. So it already has its own footprint. So we don't need to assign it again. So now apply, save schematic, and continue. Okay, click on this and click OK. So you see, all our footprints have been assigned to the specific components that we want. Okay, one more thing. Let me again go to the footprints one. Yeah. So here you see there is this footprint, right? We can right click on this and view selected footprint. So we can actually see the footprint that we want. Let's say we don't know which footprint we want to assign to our component. So we can actually go to that footprint option. Let's say I want a register THT. Here this. So there are different registers here. So here we can view selected footprint, and we can actually see how it looks from like this. Also by trial and error, by looking at every single one, we can find the footprint that matches best matches our requirement, and click here. So for this, let's say I want to see this one, capacitor one. So there are different capacitors. If I click on this, you can see this is the footprint for the polarized capacitor. Also, if you click on this 3D viewer, then you can see that the capacitor appears here. Okay, you can play around with this if you want, and I'll close this as well. All right. So now we have already assigned the footprints to each component. We have designed our schematic. Now we can move on to the PCB design portion. So from here, you can see the green symbol is there on the upper panel. If you click on this, then it will take some time to load. And yeah, here we are in the PCB designing canvas. See, you see this is a blank canvas, and this is almost similar to the previous one, just in darker theme, I guess. So here we will go here to the update PCB from schematic, this symbol, and click on this. By clicking on this and update PCB, close this, you will see that all the components are appearing here. Just place the cursor wherever you want to place the components and click it. You see all the components have imported into the PCB designer canvas. Now we'll be arranging each component. This might seem overwhelming at first, like which component will go where. For a more complicated circuit, it will be even more horrible. But with practice, I guess it will be easier. So let me first divide all the components. So R1 should go here, right? Side. J1 should remain here. J2 this side. J3 will go this side. Okay, so for this unpolarized capacitor, I think I made a mistake. I can go to the footprint design and so here you see the footprint for the unpolarized capacitor has been imported. So we'll take this and place it here. Some here. So this portion of circuit design entirely depends on you, how you can optimize the placement of components and how you can uh, minimize the required area. Here you can click on each symbol and press R to rotate them. I will be placing it here like this. The closer the better, because we want to minimize the area and make the circuit more compact, right? So I will be placing them like this. Then this one, press R to rotate them. I will place it here. And then this capacitor. I'll put it here. Yeah. Next, we'll these components. All right. So here you can see we have already placed the symbols that we need in the correct position, footprints, and I think this one is rotated. So here you can see there are some small thread-like lines. Just try not to overlap them with each other. See here there is overlapping line, so we will have to trace the path from the opposite side to here. Okay. So try to untangle each of these threads or lines, and then we will be good. So after this component placement, we will go to this track width and edit predefined sizes. Here we can add the value, and the width of the track usually depends on the current rating. So for this specific circuit or for this specific current rating, we will be using 1.5 mm. So click type 1.5 and then click OK. You can see there is this copper type. Okay. So usually the PCB has two sides, right? One is the front side and the other is the back side. The front side is where the components go, and the back side is usually the side where we place the copper traces. So here you can see there is FCU and BCU. FCU stands for front copper and BCU stands for back copper. So we'll be using this because in this specific case for this gate driver circuit, it is a single layer PCB. So we don't really need it. We can use either of them. For more complicated circuits, in order to tell the PCB manufacturer that this side is front copper and this side is back copper, we will be using different copper for different purposes, right? But in this case, as it is a single layer, we can use any of this. So I'll be using this back copper. Then, okay. So I'll click on this root signal track. If you click on this, then you can go and click on any of the terminals. If you click on this terminal, Kicad will actually show you where this terminal goes. Okay. So you can't misplace it. I can't connect this to a wrong terminal. See, I can't connect to any of the wrong terminals. So Kicad doesn't allow you to place connections between wrong terminals. That's a nice feature for it. And I will connect here. So you can go ahead and connect every single connections. Sorted this.
Sir, your video paused.
My video is paused.
Yes.
Okay. Let me see. Now is it visible?
Hello. Yes, sir. How this schematic is drawing with, this wire?
Okay, yeah. Again, I'm telling. So let me delete this. So here there is a icon, right? Route signal track. You can see this. You can click on this, and when you go to this any terminal that you want to connect, after you click on this, Kicad will show you where this terminal will go. You can't misplace it. I can't connect this terminal to the wrong terminal. Kicad will show me where this terminal will go. So I will just click on where it is showing and it will connect it. Yeah. So next, we will go ahead and click connect every single one. Okay, so I think there is some internet issue, so it is going a bit slower.
Sir, one overlap is there, na? Hello?
Yeah. So
Sir,
yeah.
our wire connected between R2 and TLP. One overlap is there, no?
R2 and TLP.
TLP, yes.
Yeah.
How
So that's
to?
why yeah. So see, this is the TLP, right? So this is a microcontroller. So we can take the trace from between them. Correct. This is a component. It will be placed on upside. It won't be obstructing this path. Correct. You
Okay,
get
sir.
it?
So
Like
the
the
wire
component is
comes.
placed on the PCB. Yeah.
Yes.
The component is placed on the PCB, so we can from below we can take the path. Correct. So it
Okay.
won't be obstructing this connection.
Okay, sir.
Let's say there are multiple interconnections, right? So in that case, we can use both this FCU and BCU, but for that we will need sophisticated PCB printing like machines and all. And for this lab for lab purposes, for printing on in simple labs without heavy equipments, we can just go for single layer PCB.
Okay, sir. Okay. Sir, all the connection are in the bottom, na? What you have connected in this circuit?
All yeah in here.
Okay, sir. Okay.
Yeah. Okay. So now we have done the PCB designing and we have already connected all paths to each and every terminal. So from here, we will go to this print option. You can also see the 3D view. You can see after print connecting everything, see how your PCB is looking. You can go ahead and play with it if you want. So I will close this and I'll go ahead and print this. After clicking on print, you can you have to check from here included layers, right? So here we are using this BCU. Okay. Before printing, I will also add an area for this. So for area will basically mark the edges of the PCB. Let's say you are sending this PCB to a PCB manufacturer and you want them to know where to cut the PCB. So you can use this area option. Click on the point, click OK. And then you can draw an area like this. Okay, so the area has been drawn and you can adjust the area so that the PCB manufacturer will know where to cut the PCB. So he will cut it in this shape. Okay. You can also sit here. So for this one actually we have to use this edge cuts. You see there's edge cuts, you use that, not the front copper. And then again I will go to that area symbol. Okay, done. Yeah. So here we are done with our PCB designing. Next we will go to the print option. After printing, so in the included layers section, to select all the coppers that we have used. Here we are using the back copper as well as the edge cuts. Yeah. So here in this way we can design any PCB that we want. Yeah.
Hello, sir. So what is the name of edge
Yeah.
cut? What means it?
Edge cuts are basically see, these coppers are not actually the physical things. Those these copper layers that we are seeing. These are actually to tell the manufacturer that what we want, what we intend. So by edge cuts, the manufacturer will understand that he has to cut the PCB from here. Got it?
Okay. Okay.
Yeah. So we have included the edge cuts and BCU, right? Or FCU we have included, not BCU.
Oh,
And then
if sir we have
yeah.
if sir we have more connections and there's the overlapping, then we will use front below
Yeah,
or bottom or front both.
Yeah, we can use both back and front. Okay. So for front, it will print on the upper surface from where the components are added, and for back, it will print on the bottom surface. Okay. So here we will back copper and the edge cut. So we will select those and then click on print. Before printing, we have to see some more things about Kicad. Okay. So until this, everyone is okay. So as I said that there might not be symbols available in the library of Kicad. Okay. So we will try to make one own symbol, our own symbol. Chosen this Atmega 320. I hope we all are familiar with this controller. Can anyone tell where this controller is usually used? Okay, actually this controller is used in yeah. Hello. Okay.
Hello, sir. Your
So
voice is
this
not
controller,
clear. It's cutting.
my voice is not clear.
Sometimes it is not clear.
Okay, I think there are some issues with the internet. And now clear?
Yes, sir. Yes.
It's okay, but I think in some computers may not be. I don't know, some places. Here it is okay, sir. We are in Hyderabad.
Okay, fine. That's okay. No issue. So you can see that this is the microcontroller symbol that we will be trying to design for a custom made symbol. As I said, some symbols might not be available in the default library of Kicad. So for this Atmega 328P, these are the pin out. You will need the data sheet of this controller actually. So you can go here and click here. Then we'll go to symbol editor. And see this symbol editor is here. If you click on this, you will land on this page. Okay, for this symbol editing. So from here, you can go to this file section and add a new library. Okay, so here you will be prompted to whether you want to add the library in global section or project section. So if you will click on global section, then it will okay. If you have done programming, that any kind of programming, that you know what is a global variable and a local variable, right? Global variable is something that you can use in any function, and local variable will be specified to the specific function. Similarly, here by choosing global, we will be making the symbol available to every other project, not just this specific project. And by clicking on project, we will limiting the use of this symbol that will create to this specific project. So for now, I will click on project and then click OK. Now I'll give give a name of my library. Let's say I'm telling Atmega demo, and then click save. Okay, so here's my folder is created. Click on it and then click on new symbol. Then it will ask you to give the name of the symbol. I will just go and give it Atmega demo, let's say. Then we can give the reference, like I said previously, that there will be R1, R2. So similarly, there will be default reference designator. Let's say we're adding this symbol 2 times in our um, schematic, then it will be read as U1 and U2. Okay, so this will be default reference designator. Keep everything as default and click OK. Then you will see that this U appears. Now what we will do, we will add the pins. Okay, there are 28 pins on this micro. Adding all the pins here. So go to the pin table and click here. So after you click, you can click on this plus sign, and then now you can start adding the number of like the different symbols for it. Okay, different pins for it. So if you can go here, you can see there is at pin number 1 there is PC6. Okay, so from here you can give pin number 1 and name of the pin will be PC6, right? Then there is electrical type. So basically in electrical type, you will have to specify the pin. It is an input pin, it is an output pin, it is a directional pin, or it is a power pin. So there are different pins options. In general, if you know about Arduino a bit, then most pins are bidirectional. That is, we can read and write, we can perform both read and write operations on every single pin. So I'll go and put it bidirectional. Line type will be graphic, and then we'll add another pin number 2, and let's say that is pin number 2 is PD0, right? So click on this and type PD0, and it will bidirectional. Again, add third pin, and it will be PD1, PD1, and then next. So like this, you can add all 28 pins. Let me show you a different electrical type of pin. Like we will be adding VCC and ground. Okay, so for that, the VCC was at pin number 7. So I will give here pin number 7, and then this will be VCC, and the electrical type will be power input. Okay, from here power input, output power input. Okay, then next it will be ground. So ground was pin number 8. So from here I will type G and ground, and it will also be power input pin. So now if I click on OK, then you can see all the pins appears here. So you can populate this entire screen with all the pins that you want, all the 28 pins. And now I will create a rectangle. Okay, so let's say I want to create a rectangle here for my symbol. Okay, so I created this rectangle. If I'll click on this and then double click on this, I can customize it according to me. And let's say I want to fill it. Okay, so this is how we can create custom symbols for our different components that we want. So you can go ahead and type all the 28 pins in this table from the data sheet. And after completing this, you can click on this add symbol to schematic. If I will click on this, then that symbol will be added to my existing schematic that I was working on. Okay, for now we don't need this, so I will be deleting this. And after you have created your own symbol, usually you will find, let's say there are 28 pins, right? You will find another microcontroller that also has 28 pins, and you will take the footprint from that microcontroller and you will paste it here. Or you can also find the footprint. Most of the IC manufacturers, they specify the footprint in their data sheets. Okay. So yeah. So after this, we'll go to yeah. So up until this, we have designed we have seen the buck converter. We designed the gate driver circuit. Now, here we are giving 0.5 duty cycle or any other duty cycle for that matter, and we are driving the buck converter, right? We gave 0.5, the voltage is cut in half. We gave, let's say 0.25, voltage is cut in 1/4. But let's say we want a closed loop system. We want exactly 40 volts, or we want exactly 30 volts. So what we will do? we will make a closed loop system. So for closed loop, we need the output voltage and current, right? For current loop and voltage loop. So for the output voltage, how will we measure it? By using voltmeter. But how will tell the microcontroller that what the voltmeter is reading? Right? We can't do that. So for that reason, we need a voltage sensor. So for voltage sensor purpose, we will be using NIT-25P. Okay, this voltage sensor IC. This is a closed loop Hall effect voltage transducer. Okay. So how it works? Let's see. This is the internal circuit diagram of this voltage sensor. You see there is a input coil and there is an output coil. Okay, or primary and secondary coil. So and there is a Hall effect sensor. So whenever there is a voltage across this input coil, then there will be a flux produced in this area. Let me. Yeah. So you can see there is this input coil, and whenever the voltage appears across this input coil, a flux will be produced in this section. So that flux will be sensed by this Hall effect sensor, and the Hall effect sensor will generate another pulse that will flow current from this secondary side. Okay, from this, he will be giving positive input, 15 volts, and from this 15 volt, another flux will be generated in this section in such a way that it cancels out the primary flux. Okay, so until the flux in this section is zero, this Hall effect sensor will increase the flux. Okay, the point where the flux is zero in this section, the current in this secondary will be proportional to the primary. Okay, so this is the basic working principle of this voltage sensor. Yeah, so next we'll go. So these are the design parameters. Okay, so we want to add a resistance RM, right? In order to calibrate. Let's say we are measuring 50 volts and we want to bring it to 5 volts. So how will you do that? We will add a resistance. So how will you calculate that resistance? If you'll go to the data sheet of this LV25P and you'll scroll down a bit, you'll see that the primary nominal RMS current is 10 milliamperes and the secondary nominal RMS current is 25 milliamperes. Okay. So here, the primary current is 10 milliamperes as we saw from the data sheet, and VP is a voltage that we are trying to measure. So we are trying to measure 50 volts. So that is VP, and the the current rating of the primary is 10 milliamperes. So we will get the primary resistance that will be 5 kiloamperes, 5 kilo ohms. Okay. Next, we will try to calculate the RM. Right. So here we calculate the R1. Now we'll calculate RM. So for RM, we need the 5 volts that we want to convert it to. So basically, if there is 50 volts in the circuit, then the microcontroller will read 5 volts. Okay. So by from the software, we can convert this 5 volts to 50 volts by multiplying 10 times. So let's say the actual voltage on the circuit is 25 volts. So the microcontroller will read 2.5. Okay. Then we will multiply it in the software by 10 to get 50 volts. So that the microcontroller will know that it's 50 volts. Got it? So for secondary side, we have this 5 volts, and we will divide the rated secondary current, which is 25 milliamperes, and we'll get 200 ohms. So from here we saw that the input resistance is 5 kilo ohms, and the output resistance is 200 ohms. Okay, and you can also calculate the input power and output power. V square by RP. Okay. All right. So this is the circuit diagram that we will be using for closed loop voltage control. Okay. That was for the voltage control. Next, we'll move to the current sensor. Okay. The basic functioning and working of both the sensors are pretty much the same. It works on the same principle. There will be input current, and this input current will be proportional to the output current. Okay. So from here, there is an input current. Here we are interested in finding the number of turns in this. Okay, this will be acting as a current transformer. So we will be trying to find that. So the secondary current, we will have to find the secondary current, right? So the secondary voltage is 5 volt that we want to reduce it to that, because the microcontroller can read 5 volts, correct? Yeah. So for this circuit, we are assuming the output resistance to be 125 ohms. We can find this from the data sheet. Okay. Go here and open this data sheet. Yeah. So here you can see that there is this for 50 milliamperes maximum. The R minimum to R maximum is from 50 to 160 ohms, right? So from here we are choosing a resistance value that is 125 ohms. Okay, so here we have chosen our resistance to be 125 ohms. So the secondary current will be 0.04 amperes. Now, by MMF balancing, that is N1 P1 equals to NS into IS, we can find the number of, we know that the secondary number of turns is 1000. We can see this from the data sheet as well. It is present in the data sheet only. See, this is the number of turns, secondary number of turns, that is fixed. Okay, we don't have to, we can change that. So this is fixed. From here, we'll calculate the number of primary turns that we require. That is NS, that is 1000, multiplied by IS, that we calculate 0.04, divided by primary current. And primary current, nominal current also, that is, it is present in the data sheet. You can find that there are 4 number of turns required if we want to measure 10 amperes. Okay. So yeah, that's it for the current circuit. Yeah. So with this, we mark the end of the entire PCB design, and now we'll move on to the fabrication portion. Yeah. So from here, let me close this. Yeah. So here you can print this circuit as you want, like you can print it. Usually we'll print this circuit on a photo canvas, like the glossy paper you have seen that we use for photographs, right? Now, home photographs. We'll print this circuit on that. Okay. So for printing the circuit, there are 2 ways. First, we can either send this file that we have created to a PCB manufacturer, and they will return you with the PCB. But those are very costly, and for prototypes, we can't really use them, because let's say there is some fault or there is some kind of mistake in your PCB. So you can't be sending them again and again, and it will be too much cost and too much time consuming. So for that, we will be using our lab in order to create some PCBs. Okay. So for that, I will be in the next processes. So here you can print this and normal how you print from a printer on a normal paper. Okay. So already printed. So I won't be printing this, and I will close this inside. Okay. So yeah. So now we are done with the Kicad section, and now we'll moving on to the fabrication process. Okay. So you see, we have already printed the circuit that we designed in the Kicad here. It is we have printed this on a glossy paper, as I have explained, the photo paper that we talked about. Yeah, on a thin glossy paper. So after printing, you have seen these kind of copper clad plates, right? These are available in different electrical stores. You can buy them and use an inkjet printer. Laser jet, or they will carve on this paper, and this print this ink won't come onto this copper clad. Okay, so make sure to use the inkjet printer and use a glossy paper. Print this PC, this designed circuit on the paper. This is a printer will be used. Okay, so next we will place it on this copper, and Okay, by placing on this, and we'll take a electric iron, and press this paper over this copper. So what it will do is it will imprint the ink from the paper onto this copper plate. Okay, uh, and after imprinting this, after some while removing this paper from over this, you will see that all the PCB design or the circuit will appear on this copper plate. Right, you can see this here. You can see here that the ink has appeared on this copper plate. Now you can go ahead and put this in a container. Okay, and then we will put some ferric chloride over this.
Sir, hello.
Yeah.
Sir, we have to take the print of that PCB we have designed on the grocery paper, na?
Yeah.
And we have to paste on this copper plate, na?
Yes, paste it on like put it on the copper plate, and then take an electric iron and press over it. Yeah, so
Okay,
that
okay. And then remove.
yeah, then we'll after some time we'll remove the paper. So you will see that the ink from the paper has transferred to the copper plate.
Okay, sir.
Like this here, it has transferred here. Okay. So
Okay.
now we'll
Then what happens to
put
the
some
glassy paper, sir?
glossy papers are like the photo papers that we use for photographs.
It can be used in
it is to be only one time use.
Yeah, it is for one time use, because after
time
pressing
use.
iron, this paper will be destroyed almost.
Okay. Thank you.
So it can be used in any printer.
No, for laser jet printers only.
Laser jet.
Yeah, so that this
So inkjet printer you said, right? Inkjet printer, so ink is transferred.
You said
Not
previously you said, sir, inkjet, na?
yeah, sorry. Yeah, my
you said
mistake. I
inkjet
got a bit confused. Yeah. Inkjet printer you use to transfer this to on this. Okay. So
Okay.
after this, you will see that the ink has appeared on this, and then next, these are the videos that we have taken in order to print this. You can see from here. Okay, so here you can take a iron and then press it over this. Then after pressing, you will dump some ferric chloride over it, like this. Yeah. So
Chloride,
after
sir.
coating, yeah. So after
Okay.
coating this entire PCB with ferric chloride, wait for 15 minutes or something, right? So that the upper layer of this copper will be dissolved. See, we have printed the ink on the copper, right? So the unexposed parts, which are not under the ink, those portions will be dissolved away by this copper ferric chloride. Okay, and the unexposed part, the circuit traces that are under the ink, those will remain intact. Got it? So after this, we'll after like 15 minutes, we'll put a very small amount of water. Don't dilute the ferric chloride. Just a small amount of water. And then we will like wash it away. All the coppers that are dissolving from the surface. Okay. So
this is available in the market, na, ferric chloride, easily available.
yeah, this is available in the market.
Okay.
You can find it in the market,
Yeah.
or you can find from online stores as well.
Okay.
Yeah, etching solution you'll get for 50 rupees a pot.
Yeah. What? Okay. So after doing this, so after all that, we will left with this PCB. See, the copper underneath the ink has remained intact, whereas the copper outside the ink has dissolved away. Okay. So next we will drill the holes where the pads are required. So here you can see this is the position for the IC, the TLP250 IC, this one. And then this is the input terminal. There was a resistor here, right? So this is basically the PCB.
Sir, hello.
Yeah.
Sir, this plate contains both side copper, or only one side?
This
You
is
have
only
to
one
use
side,
this.
no?
Okay, sir.
See, this is only one side from back side. If I would have used the front copper, then there would have been circuits on this front side as well, right? There is no tracing on the front side.
I'm asking, sir. I'm asking before you are used in the ferric chloride.
Yeah.
Copper is on both sides, na?
No, copper is on single side only.
Okay, sir. Okay.
Okay, copper is on one side. For both sides, it will actually you will have to send to that PCB manufacturers. Okay, those are not possible with this kind of techniques. Okay, next we'll place the components and solder it. So after placing all the components and soldering, you can see this is the final PCB. And yep, we have successfully designed our circuit. And finally, we have our microcontroller. Here we are using Arduino for that purpose. So if you are familiar with Arduino programming, that you might think that this code that you are seeing, this is not your typical Arduino code, because usually you code in software level, right? You will define some pin mode, like here we are defining this pin number 9 is output, and then we will move on to the void loop in order to set like 50% time pin number 9 will be high, and then wait for some microseconds, and then again it will be down, and that way we usually do. But there is a problem in that configuration, is that with the increase in frequency, the pulses that you will get, won't be perfect 90 degrees. The rising and falling edges will slant a bit. So it won't be giving you the proper PWM signal. For that, what we will be doing is we will be hard coding, like we will be putting the code on a hardware level. Okay. So here you see that I will be explaining this code. So first we are defining the pin mode 9. Okay. For the pin number 9, we are defining it as output pin. So basically we will be getting the PWM signal from digital pin number 9. Okay. Next, here there is no interrupts. If you are familiar with the concepts of microcontrollers, then you know what are interrupts, right? Let's say a microcontroller is doing its own job. For example, it is sensing some data from a sensor. Okay. So, and there is a keyboard attached to the microcontroller, and the user pressed some key on the keyboard. So what will the keyboard do? The keyboard will send an interrupt signal to the microcontroller. The microcontroller will halt its ongoing processes that was reading the data from the sensor. It will stop reading the data from the sensor. It will acknowledge the interrupt from the user, and then it will again resume its own task. Okay. So basically what we are doing is no interrupts. So basically from this point onwards, microcontroller won't be taking any kind of interrupts. If you have connected any keyboard or anything, or any sensor or any data, it won't accept anything. It will only execute this inside program. Okay, the program underneath this. The next, there are this two lines. This TCC R1A. These are the timer control registers. Okay. If we know about microcontroller, there are different registers, right? So this is basically a timer control register. So we'll be comparing each timer with some time, like okay. So the frequency of this microcontroller is 15 megahertz, 16 megahertz. So according to that, this will produce some like 1 by 16 megahertz. So that will be the time period of each cycle. Okay, and we will be comparing that with each like our required frequency, that is 50 kilohertz. Okay, and from that we will be giving high and low pulses from this pin number 9. And finally, we will again resume the interrupts. So this is the total like program. We will dump it into the Arduino and already dump this code into our microcontroller, and from here. Okay, so just a second. So this code, I think many people are not familiar with this Arduino coding. So you can also use MATLAB and MATLAB tools in order to program this. And yeah, so now we'll be showing you the hardware design. So just wait. So am I audible?
Yes, sir.
You're audible. You can see the
Yes, sir.
camera. Okay. You can see the camera, right? Okay. So here you can see this is the entire buck converter setup. So this is actually interleaved buck converter. But what we have done is we have removed one leg of it. Okay. So we have removed one of the legs. So it will be working as a normal buck converter. All right. So from here you can see this is the microcontroller that we are using. Then there is a power supply for the gate driver circuit. 15 volt, because we need the 15 volt power supply to the gate driver, right? Then we have this load resistance. We have this voltage supply that we will be using to test this, and this is a CRO for seeing the waveforms, DSO. So yes. So now I'll turn on.
Sir, your screen is not visible, sir.
Screen is not visible.
Yes, it's visible. Screen is visible.
Okay. So here you see this is the gate driver circuit. This small one. This one I'm. Yeah, this one, and there are two gate drivers actually, but one is non-functional because we are using this as a buck converter. This is actually interlude buck converter. So from here, for this supply, we are giving it from this power supply module, which is fed from this transformer. There is a rectifier here, and it will down the voltage to 15 volts. Okay. From there, we are giving it to this gate driver circuit, and from the gate driver circuit, we are controlling this switches. From this side, you can see the switches, and yeah, from here we will be supplying the voltage. So let me increase the voltage. Let's I'm giving around 20 volts. So you can see on the multimeter that we are getting 10 volts output. Okay, here we are giving 20 volts as input, and we are getting 10 volts as output. So this is an open loop system. We have programmed the microcontroller to output 0.5 duty cycle, and yeah, it's this is how we can design a complete buck converter with this circuit. Now I'll show you how the PWM from the microcontroller. Okay, yes. All right. So here you can see we are getting the pulse. So this is the pulse coming out from the microcontroller. Okay, here you have added this to this CRO, and you can see this is 50% duty cycle. So you are getting the exactly half voltage from the input side. And yeah, that's it for this demonstration. I will be heading to the PPT, and I can take any questions or queries you have.
Okay.
Hello.
So,
Hello.
Shaswat, I think your presentation over. Am I right?
Sir, one question.
Good morning, sir.
Shaswat, am I audible? Please unmute
Yes,
yourself.
sir.
Okay.
Yes, sir.
So, kindly conclude your presentation complete. Am I right?
Yes, sir. Yeah, completed, and
So,
thank you for your questions.
yes, yes. I'm requesting all the esteemed participants, if you are having any queries, please let us know. We are happy
Good
to
morning, sir.
respond.
Yes.
Good morning. Yes, can you?
Nice presentation, sir. Sir,
you.
I'm having one doubt. Single layer PCB design or multi-layer? Which one is preferable, sir?
Actually, multi-layer is preferable, but for multi-layer, we will have to go with PCB designing manufacturers, right? PCB design manufacturers like JLC PCB
Yeah.
and all. But let's say you are making a prototype that, so you'll be having many alterations. So you can every time you can send it to a PCB manufacturer. That will be not that won't be cost friendly, and it will take many times because you will send,
Okay.
then they will reply. Yeah. So this is a single layer process. In this process, you can do it multi-layer because this copper cladded plate, it is only clad on one side. The other side is not conducting. Okay.
Okay.
So yeah, that's
Thank you, sir.
yeah.
Hello.
Sure. Yeah.
Hello, sir. In a similar manner, we can design gate driver for any DC-DC converter, no?
Yeah. Sure.
Okay.
So
Okay.
not only gate driver, we can design any PCB that you want. Actually,
Power
there are many
circuit
things
as
in
well as
this.
control circuit. Yes.
Yeah, power
Both.
circuit as well as control circuits.
Both we can design.
Okay. Sir, what you have shown a sensor. Sensor we also can design in this.
Yeah, of course. This
Okay.
voltage and current sensor, you can design the circuits on in this this you can design the same way. This LV25P is also available in the Kicad. This IC.
Okay.
Yeah.
Okay. Thank you.
Anything else?
Is there any other query? Any other queries? Please let us know.
Sir, I have a doubt,
Okay.
sir.
Yes.
Yeah.
So you are designing an buck converter
Yeah.
and then low side driver, sir. Actually, it is an you should have to design a high side driver, sir.
Sorry, I didn't
Because
get it.
source is floating now, sir.
Source is floating. What does that mean? I think I'm not aware of.
Can you please elaborate your question? Means we are not able to get your question.
Yeah.
Hello.
Yeah.
Can you please elaborate your question? Hello. Where is the left? Please ask your question, madam. If you are having any doubt, please let us know. We have to start the next session. Actually, we scheduled by 11. So we are going to conclude.
Can give us 5 or 10 minute break. Hello.
Yes, we can give 5 minutes
Sir.
back. Okay, no issue.
Okay.
Please, we need to conclude it. If you are having any queries, please let us know. Some of the professor raised their hand, but didn't ask any question. Okay, then we are concluding the session. Thank you, Shaswat and Suvankar, because
Thank
session
you, sir.
was, I think session is very important. I mean, it was good, and I think all the participants learn a lot of things from the session. Okay, so
Thank you, sir.
yes, two participants raise your hand. Paul Matthew, please ask us what is your query. You have raised your hand, and Professor Madhumita Das Sharkar. Please raise your, you have, both of you raise your hand, but didn't ask the question. Please let us know. You're having a doubt, please let us know. Please unmute yourself and ask us.
Hello.
Yes.
Hello.
Hello, sir. My question is that the driver designed by you is an low side driver, sir.
Low side means, what is the meaning of the low side? I'm not able to get it. Your point.
So the ground is connected to the source, sir.
How
If it
driver
is an
is
your
already
source is
isolated.
actually, if it is a buck converter, your source is floating, sir. So the power supply ground should be shorter to the source.
Why floating? I'm not able to get
Yeah,
it.
on
Can
TLP
please-
circuit, sir. Yeah, sir.
The source is floating. No, it is isolated, right? Input side
Isolated,
is
no?
isolated.
Power supply is
Yeah.
there.
Sir, it is an isolated, but driver power supply should be shorted, sir, if you are using this circuit on an buck converter, sir.
Okay,
No.
sir, let me clear that out. Actually, you are right, sir. For a different other
Sir, if it is an
driver
high side
circuit that
driver, you should have to use an
I
bootstrap
got
diode
your
and bootstrap capacitor, sir.
yeah, I got your point. But we need the high side driver circuit for the buck converter as the switches are floating. I know, but in this case we are using a TLP 250, right? That is isolated from the input from the output. That is on individually to act as a high side only. So you can use it. There are
Actually,
other
this is perfect
drivers
for
available.
an buck converter. This driver is perfect for an buck converter. Sorry, boost converter.
Yeah, but it is isolated from the input to the output. So you can use for a single individual triggering circuit, you can use TLP 250 also. If you see the configuration of TLP 250 now, it is isolated from the input and
It
output.
give an isolation from microcontroller and to the driver side, but the
See,
driver power
we are
supply should be
giving
get shorted with the power converter supply. Okay, sir.
See, we are giving supply from the microcontroller to the driver circuit, and the driver circuit TLP 250 output side that will be connected to the switch, right? So the driver microcontroller side is isolated from the of that switch side through the TLP 250. If you see the TLP 250 configuration, it will know. You can see the input is isolated from the output side. So for a single switching, you can use a TLP 250. If you use to use multiple switching, then there will be a problem. For a single buck converter, if you want to switch through the TLP 250, it is okay.
Are you getting your point?
Yes, may I ask one question? Actually, my mic is not working. That is why I raised hand, but I am not. Am I audible now?
Yes, ma'am, you are audible. Please carry on.
Yes, yes. Actually, my first question was the buck converter that you have designed for for us for a specification with a specification, or it can be kind of general. You have started this for driving a voltage of 48 volt.
No, it's
Your load is what is your load actually? That is why you are converting this. That is
volts.
one of the most important thing that depending on that our buck converter specification, because you are using TLP. What is the maximum saturation voltage of that driver?
general viewer who take it, the main
Madam, I'm telling you one
presentation.
point. Just Shashat, just one moment. Madam, okay,
yes.
so driver, there is a power supply. Okay, so that will be your maximum saturation voltage. So maximum
Yes.
saturation voltage means you are giving some biasing voltage to your any of the IC.
It is okay, but that what is that maximum saturation? What is the power supply of TLP?
That is plus
250?
minus 15. No? This is 15 volt as
15.
a
Now
connected.
my
Yes.
question is, if it is 15 volt, then you are the next stage is your 48. You are driving the battery for the with the buck converter, that is the generating the solar module,
No,
which
buck converter driver getting generates the gate pulses. That gate pulses you are giving to
PWM.
yes, that gate pulses means it's a PWM. That will be feeding to the
PWM.
power circuit switch. Then power
Okay, so
circuit,
that switch
there
is
is
only
a
required
resistive load.
10 to 15 volt amplitude, not more than that.
That is your PWM voltage range. Am I right?
Range. Okay.
Yes.
Now you can modulate that according to your need. Now my
Yes.
question is, when you are switching your speed, that is Arduino 16 megahertz is sufficient, or it because your square pulse it may not be coming because of this propagation delay or kind of thing, gate delay. So in that case, may we convert it to any other high-end uh, maybe Arduino or 240 megahertz. I think 16 megahertz. There is one Arduino Uno something. The number is I forgotten, but there is also 240 megahertz pulse. So may we use that? One question is that then my target is to only you are designing this buck converter for PWM generation.
Yes, this is a demonstration. In the
Okay.
demonstration, we are showing that how to generate the pulse, and after getting the pulse, we are feeding that pulse to the power circuit, and how the output. We are giving 20 volt as an input and 50% duty cycle. We are getting in open loop. Okay, so in open loop, and how the 10 volt is coming. And main thing is that how the fabrication's done and all those things. Everything
Mainly
will be
focused we are
demonstrated.
in PCB design mainly.
Exactly, yes, and how the basic things are there, because in this course different types. Some of the participants they want to know how to generate the PCB, how to develop the PCB, and how the entire thing will be carried over. Right? Because all the converters are designed in our lab itself. Okay,
Yes,
so
yes.
from the crash level to up to testing level. Okay, and the product after that prototype design. Okay, so
Now
that's
my
why this is
question
the.
is, now my question is, if there is any converter that has to be decided at real time. So if data is changing and we require to have our pulse width changing required at real time, then any kind of design there is, or it is only for PCB only, with a particular specific converter you have taken and it is implemented in PCB. Is it?
Yes, yes. Here only we have designed that internally back converter, and using one of the one of the switch, and there was using the output, and that's it for this study only. Okay, and you are changing. You are asking that the closed loop operations. I think so, indirect way. So the closed loop operation is not showing in this case. Okay, and yesterday evening they have demonstrated the real-time operations. If the YouTube link is already available, you can see they have demonstrated the integrated system. You can also see where the data are varying and how those things are handling power. Okay, all those things. So you can check it for the YouTube video link. Again, I will share. Okay, so you can check it from there also.
Thank
Okay,
you.
thank you.
Now in PCB design, one of my question is, you are
Madam, yes, yes, because we are going to almost, our time was from 11, so it is 11:10. So in next session, and again we are taking the question. Definitely. So again, we will take a lot of again question answering session. There will be there. You can also ask. You can write the question. You can, because in our lab all are demonstrating. Okay, so next session you can also ask the same question. You please note it down. We will answer all those things. Okay. Let us start the next session. Then we'll answer the end of the next session. Okay, madam.
Okay.
Okay, thank you. Jaydev, are you ready? Okay, so we are going to conclude our fourth session. Okay, so thank you, Shashat.
Thank you, sir. And yeah, thank you, everyone. Thank you.